Welcome to the Word Problem Intervention Program. We're so excited to have you here. As you move through this program, you'll have access to a wealth of free materials and resources. Some materials will be fully accessible, while others will be partially available. But either way, you are leaving today with abundance of resources to support you along your word problem journey. The Word Problem Intervention Program is a schema-first intervention, meaning we identify the type of problem structure before anything else. The program is built in a layered system. We begin with the assessment to find the schema. From there, instruction unfolds into deliberate scaffolded layers. Students receive multiple rounds of instruction and guided practice before they're ever expected to solve a problem independently. Now let's go through all the free resources that you'll be receiving today. The first thing you'll receive is access to 2 diagnostic assessments. The addition-subtraction word problem assessment covers kindergarten through grade 5, starting with numbers up to 10 and progressing all the way up to 1,000. The multiplication division word problem assessment is designed for grades 3 through 5, beginning with basic facts and extending up to multiplying 2 and 3-digit numbers. These tools help you identify exactly which problem schemas or structures your students are struggling with, so you can target your instruction where it matters most. Each assessment also includes a progress monitoring scoring, so you can document where students start and track their growth over time, making it easy to see what's working and share that progress with others. You also will have access to our schema read-alouds, which these are short stories specifically about each schema that you go through and read with your students to teach them in a fun and interactive way about each schema that they're going to be learning about. And there's 3, you'll have access to all 3 different books, one for total, which would be part whole, one for change, and one for comparison. Before students ever open up a workbook, they will have already been exposed to the schemas in a variety of ways. Users will have access to part of the entire schema poster library included in the program. These are visual tools designed with minimal text, allowing students to develop a clear structural understanding of each schema before ever encountering a full word problem. By introducing the schema visually first, students build a solid conceptual foundation, understanding how each problem type works and what it looks like, before being asked to read, dissect, and pull numbers from a problem. This visual approach ensures that when students do engage with full word problems, they are not learning the structure and the reading at the same time, but rather applying a schema they already understand. Teachers will also have access to the Developing Schema resource, which serves as another layer of schema development that comes after the schema posters. Before students are ever asked to read or solve problems on their own, this resource ensures they have a deep understanding of each schema. The process begins with numberless word problems, story problems that present a context without any numbers. This is intentional. By removing the numbers, students are not distracted or overwhelmed by computation. Instead, focus entirely on understanding the context and identifying the structure of the schema. Once the foundation is established, the same problem is revisited with numbers added in, and students then build the schema using the familiar context they already worked through. This gradual progression ensures that students develop true structural understanding of each schema before they're ever asked to solve it. The Word Problem Intervention Program includes 4 e-library books, 2 focused on addition-subtraction, 1 focused on multiplication-division, and 1 focused on multi-step problems. The addition-subtraction books cover numbers within 10 to 20 and numbers within 100 to 1,000 respectively, and users have free access to the entire first unit of both result unknown problems across both books. In multiplication-division, users have access to the entire first unit of equal group structure, which includes an inverse sequence covering multiplication, product unknown, measurement division, and partitive division. Users also have access to 1 full unit from the multi-step problems book. Each book follows a consistent lesson structure with a teacher-led opening, a teacher-guided practice session, and an independent practice component. Another free resource that you'll have will be access to our math games. If you go to our website, you can click on math games, and these are all the different math intervention games that we have available. If you go to word problem schemas and you click on that, you'll have free access to game I'll say games in quotes, but these really are lessons, things that you could use. You also can assign these for students to use as well, and there's a lot of different variations, different ways that they can work on schema. Some they're just putting the schema together with images. Others they're actually plugging in numbers and solving it, but this is a really great resource you'll have free access to as well. And finally, teachers will have access to a read aloud centered around the CUB strategy. The CUB strategy is a structured, step-by-step process that teaches students how to read a word problem, identify the schema, and work through it in a systematic way. This strategy is woven throughout all of the program's resources and serves as a consistent approach students will use every time they encounter a word problem. The read aloud introduces students to the CUB strategy in an engaging, accessible way, laying the groundwork for how they will interact with word problems across all 4 books. And the last resource you'll have access to for free is called our Word Problem Schema Guide. And what this essentially is, it's the prompting guide. It's the questions and the ways that you will teach it and give you the language and prompts and how you'll explain kids to things for the different types of schema that you'll be using too. A really helpful resource, especially if teaching schema is very new to you. It will help you understand sort of the teaching points, the vocabulary you're going to use, and how you want to word things with your students. Really useful resource for teachers who are just beginning this. So how do we instruct word problems? And so 99% of your students, they're going to have their exposure to word problems is going to be through your Gen Ed Tier 1 curriculum, okay? Whatever your math program is, that's going to be the delivery device of word problems to, almost all of your students exclusively. So Tier 1 general education math programs essentially follow really straightforward structured path to word problems. There's always some type of concept that students learn in isolation. Then after they've had enough practice, what we ask them to do is they're going to take whatever that concept or that procedure was, and we're going to ask them to apply it into the word problems because it's going to be embedded into the word problems. But think about this. Almost all of your instruction is spent on the concept or the procedure that you want them to be, fluent or proficient with. And then when students see a word problem, they're only seeing that word problem for the first time because there's math that's embedded into the word problem. So the approach that our Gen Ed Tier 1 tends to take is this: learn the concept and practice it in isolation. Then all you need to be able to do is just read the word problem, and then you apply the concept. So it really simplifies the process. Practice in isolation, read the problem, apply the concept. But when you go through and you look at surveys, and this is from one of the pieces of research that we looked at, it says when your students struggle with word problems, what are the major reasons why they're having trouble with the work? And the first one says they can read the word problem, but they can't understand the mathematical question being asked. So when you look at our instructional time, how much of our instructional time is being spent on developing the concept, right? And by the time we get to the word problem, kids are only seeing that word problem because there's math embedded to it, but no actual time ahead of time was spent on developing what word problems look like, the language and so on, the linguistics. And so we'll take a look today very closely at how our Tier 1 delivers word problems for our students, if that's necessarily working, or if that's really the best approach in which we have for our students. So now we're going to take a quick look at the cognitive processes for a word problem. So there was a study done with a large group of adults, and what it did, it gave adults a variety of problems, from very easy problems to more complex problems. And what the analysis found, or the imaging analysis found, is that 4 stages exist: encoding, which is the downloading part; planning, strategizing; solving, performing the math; and responding, typing out the answer. And this is important. It says the analysis found 4 separate stages, depending on the problem, varied in length by a second or two. For instance, planning took up more time than the other stages when a clever workaround was required. So just remember, the brain is heavily engaged at the beginning, but different parts of the brain are being used during different stages. So we're going to take a closer look at the next slide at what parts of the brain do what and how that can help us with our instruction. The cognitive process for word problems involves different parts of the brain, okay? When students are working on more equations or solving for a missing factor, things, that's more in the parietal lobe part of the brain, and that's when you're just working with numbers. And even though this may look like it's, higher level thinking and things, when you're just working on the numbers itself, the parietal lobe is the part of the brain that is engaged. However, when students are working on word problems, the frontal lobes are critical for solving word problems that oversee it. So when word problems are happening, the frontal lobes are engaged and essentially transfer information to the parietal lobes, right? And so if we take a look here at this word problem right here, and that word problem, what it requires is this formula, which is the Pythagorean theorem. All different parts of the brain are going to be engaged, okay? This is going to be in the parietal lobes, this is going to be in the frontal lobes. But it's important to understand when students are going through word problems, different parts of the brain are engaged at different times. Particularly at the beginning when the brain is most engaged, it's using a lot of the linguistic and language parts of the brain and then transferring that over. So it's important to know that, to understand that the brain is really processing the language first before it's doing anything. Then it eventually gets the information to the parietal lobes. So we'll go through today and think about, if with our instruction and how we instruct kids, are we focusing on anything that has to do with really that linguistic, that language part of the brain first, or are we mostly focusing in on just getting information to the parietal lobes? So what are the reasons students have difficulties? Now we're going to take about 3 or 4 minutes to go through what research says specifically about word problems. And the research is kind of clumped into two parts. The first part is, why do students have difficulty? The second part, and most importantly, has to do with what can we do to help them. So the first part says understanding the problem. And again, you don't have to be a researcher to know this. You just have to be a math teacher for about a half hour to understand this. But it says understanding the problem. Students often struggle to translate word or problem to mathematical terms. They may get hung up on specific vocabulary or miss key information needed to solve the problem. So the first part is they just don't understand the problem. This next part goes into, well, why aren't they really understanding the problem? And specifically, they're unable or identifying key information and operations. Students may struggle to identify keywords or phrases that signal the operation needed. They might not recognize that some key words can have different meanings depending on the context. For example, left can mean subtraction, or it also can mean remainder. Now remember, what's interesting about these two things, why students are having difficulty, this is more language-based, metacognition, comprehension-based. This doesn't have anything to do with processes and procedures yet. So what does it look like when kids don't understand the problem? They can't identify key information. Students just sometimes just won't even attempt. They know this is a problem that's different than what I'm used to. It's not just straight addition or subtraction. I'm struggling with it. I'm not even going to attempt. Sometimes you have students who attempt, and they struggle so much with it, and they eventually get to a point of exhaustion where they just give up. And then finally, which is most common too, is you'll have students who will apply a procedure or a concept that they're familiar with to a problem that that procedure doesn't apply to. So you have students, adding when they're supposed to be subtracting, or multiplying when they're supposed to be dividing, or in this case, they're multiplying when they're supposed to be adding. The next part says applying procedures. It says even after understanding the problem, students may not know how to solve it mathematically. They might lack the necessary foundational skills or struggle to apply them word or context. What it means is a student may be able to recognize a problem involves, multiplying, but the problem involves maybe a 3-digit times 2-digit number, and they don't know how to actually do that process. So that's what applying procedures has to do with. They can understand the problem, but they just don't know the processes or procedures to do it mathematically. And finally, the last one is limited conceptual understanding. Sometimes students memorize procedures without truly understanding the underlying mathematical concepts. This makes it difficult to adapt their approach to different types of word problems. So for example, a student could know how to do a 2-digit algorithm of addition or subtraction. Then they come across a problem that has that same math in it, but they're unable to extract that information and create that equation. What can we do? When you go through all the research, and there's a lot of research that's out there about word problems and what's the best way to teach it, and there's really 5 main thoughts or ideas that keep showing up time and time and time again. The first is focus on a problem-solving strategies. Teach students a systematic approach to solving word problems, like identifying schemas, drawing diagrams, or restating the problem in their own words. That doesn't mean, though, and research is also really clear about this too, if you just have your students memorize steps or try to memorize keywords, they're not going to have success because those are really short-term fixes and those don't work in the long term. But so much time in schools is spent looking for the next strategy, whether it's the rise strategy or the cube strategy or the coin strategy, and just giving kids an acronym and saying follow these steps isn't going to do much because there's so much more like layers and depth of instruction that students need. Explicit instruction on schema. This is the most important part. It says dedicate time to explicitly explain the structure of each schema and how they signal mathematical operations. When your kids understand how the schema and how the schemas work, it's going to help them understand what to do. And again, so often when we talk about word problems and what's going on in classrooms, a lot of times it's focusing on keywords. And if you memorize these keywords, you're going to know what to do. Again, those are really short-term fixes that only will work at a very low level type of problem. And then they really fall apart as kids get older, and research is really, really clear about that. Real-world connections. Whenever possible, connect word problems to real-life situations to make them more relatable and engaging for their students. This is a huge part, and this is a really big part of our program, is scaffolding and differentiation. Provide students with different levels of support depending on their needs. This could involve offering prompts, visuals, or alternative representations of the problem, and a lot of ours has to do with using schema models and drawing schema models. And the last one is practice with varied problems. Expose students to a variety of word problems with different contexts and structures to help them develop a broader understanding of how to approach them. And so often when kids are working on multiplication, they're doing multiplication word problems, or when they're doing subtraction, doing subtraction. And that's not always the best way to teach them because they're already knowing what the operation is before they do the problems. So having them experience a lot of different problems where they really have to think. And in case you're interested in any of the research, I'll just leave this up for a second. You can go ahead and write it and take a look at a lot of different pieces that we viewed and that we went through from going through everything today that we're going to present. So what we're going to do now to understand our math curriculum, how our math curriculum is today in 2024, we're actually going to take a look back at about 20 years ago. We're going to look at what curriculum looked like back then. We're going to look at some reforms and some movements and some things that happened. Then we're going to look at how that changed our curriculum, okay? So I actually started my teaching career in 2003, okay? And this is actually I still had it. I found it in the closet. But this was the math program that I used my very first year of teaching. I taught fourth grade. If you take a look at this, it's like, whoa. First of all, I looked at this. I couldn't believe that there was 40 practice problems on that. Like that, just the sheer volume of practice, I was surprised. Like, wow, we did a lot back then, okay? And if you notice, there's something that's really missing too. And what's missing? There is zero type of problem solving or word problems on this, okay? Well, let's take a look. That's just the first page, right? Maybe the first page is practice and the second page would be applying it more. And here's the actual second page when you get into 2-digit times 1-digit multiplication. So the first one had 40 problems, right? This next one has almost 40 problems on it too. And again, up to 35. And then they snuck in 2 word problems. So picture this ratio, right? About 40 on the first assignment, 40 on the second. So after 80 practice problems, they had 2 times that they actually applied it into a word problem. And then we'll take it to the third lesson, right? This is the third lesson going through practicing that 1-digit times 2-digit multiplication. And if you take a look again, another 37 problems, and then they had kids would have a stroke right now if they had to do this these days. It shocks me how much practice there was back then. Anyways, and then they snuck in 2 problems. So think, there's 40 problems, 40 problems, and 40 problems. It's about 120 problems, and there were 4 word problems on it. Then around the 2010s is when the Common Core movement came. And what the Common Core essentially said is our curriculum is not challenging our students enough. Our kids are not critical thinkers. They're not problem solvers. Our curriculum is very process and procedural oriented. There's not enough problem solving where kids are getting a deeper understanding. And so during this time, about 41 states adopted the Common Core. There were a handful of states who said, we're not interested in the Common Core, but what we will do, like in Texas, they redid their standards. They called them the TEKS, and then the STAR is actually their state test that they take. And then Florida was a little bit later in the process, but they ended up making their own standards called the BEST standards, and then their state test they take is FAST. And then Virginia ended up creating their own standards too. But whether you're Common Core or one of these states that didn't adopt Common Core, what it represents though is a redoing of your standards, right? And when you redo your standards, what has to happen? Your curriculum has to follow. So all of this was influencing 2010. So now when we take a look at curriculum, this is a more modern piece of curriculum, and I believe this is the second version of this particular math program. If you take a look at here, 8 practice problems, right? Think about this. There was a ton. There was 40 practice problems on the first one. This first one had 8, and this is the area model, which it wants them to practice. So they have 8 practice problems, and look, story problem, story problem, story problem. Let's take a look at the next page in this lesson. Ready? Story problem, story problem, story problem, story problem, or word problem, word problem, word problem. Go again, word problem, word problem, word problem, word problem. So the pendulum has swung, right? We saw what curriculum was looking like. Common Core said we need a harder curriculum, a higher achieving curriculum, a more challenging curriculum. And the thinking is if we give a harder curriculum to our students and we require them to think at higher levels, and exposing them to lots and lots of problem solving, that will make them better at math. That was the thinking. Give them a harder curriculum, the kids will follow. So now what we're going to do, we're look at some macro data. And this macro data comes from an assessment called the NEAP test. And the NEAP is a national test that's given every 2 years. It's given to 4th graders and 8th graders in reading and in math. What this allows us to do is we can look at for large trends, when there's changes in curriculum or policy. We'll see, well, did that policy have a positive effect, a negative effect, or no effect at all? And so when you take a look here, like in the year 2000, it was a 226, and then about 9 years later, the scale score was a 240. So did anything happen, or was anything implemented during that time? And actually in 2001 was the No Child Left Behind Act. Remember, this was not a curriculum act. This was more of a testing, right? Before 2000 or before No Child Left Behind, very few kids were taking standardized tests. Maybe it seems weird to say that now, but back then it was maybe only 4th graders in some states, 8th graders in other states. So not a lot of kids were tested back then. And so there was a gain in achievement. Some will say, well, it's because No Child Left Behind did a lot of testing and schools were able to adjust their instruction. Others will say all we did was turn our kids into professional standardized test takers, and they just got better at taking standardized tests. Regardless which side of that argument you're on, it's still undeniable that No Child Left Behind did have a positive impact on math achievement. So remember now, Common Core is a curriculum initiative. So the idea is this is changing, or it's a standards initiative, but changed all the curriculum and then aggressively, right? All problem solving based, deeper thinking. And so we would think this would have a lot of impact on student achievement as well, just because of all the changes that were put in place. A lot of money was spent, a lot of new programs were implemented. And so let's take a look what happened. And what's surprising is, and I know we may look here and say what happened here, and this is COVID, and we all know about that. But I really want to focus on the 8 or 9 years since 2009, where all these new standards were implemented. Because realistically, students are no better at math today than they were 20 years ago. And something we could have learned from this is just flooding curriculum with word problem after word problem didn't necessarily, well, it didn't increase student achievement. So let's take a look at how and why, because it's still hard when you compared those two curriculums. How could you have a curriculum that changed so much and yet have no impact on student achievement? So it's really hard to wrap your head around. How is it that we've had such a dramatic change in curriculum where 20 years ago students were doing so much process and procedure, right? And then now we have so in our math programs, they're just loaded with word problems. So if you take a look at this right here, and one thing is you have to point out too is, and I think most teachers know this, the amount of practice for concepts right now, for concepts and procedures, is very minimal, okay, in more modern math programs. And what's happened is, like for this one, students were learning 1 digit times 2 digit, and they're learning the place value sections method. And for this is they really only had 15 chances to practice this problem. There was the first page had 7 problems, and now they had these problems here. So now the thinking is, okay, they have these concepts, now we're going to have them practice these concepts within these word problems, okay? But think about this. When they get to the word problems, are teachers really focused on teaching kids about the schema and how the problem is set up and what it visually looks like and using graphic organizers? Or are teachers just more concerned with, well, we're doing 2 digit times 1 digit multiplication. I'm going to teach my kids really quickly to read through, circle the 2 numbers, maybe underline the question, and then go ahead and perform that concept that we're practicing. Because the word problems essentially are also, it seems on the surface these are word problem practice, but it's really just an extension of the concept because we're not requiring a lot of thinking. These students know we're multiplying 2 digit times times 1 digit. So no matter what, all I have to do is just mindlessly pull 2 numbers out and multiply them like I've been doing, okay? And that's sort of the problem with how we're doing word problems right now is there's no really teaching of the word problems. The word problems are just an extension of the concepts in which we're practicing, okay? So we could go through, and if you even look here, it says you can use your skills for multiplying 1 digit times 2 digit numbers and to multiply 1 digit dollar amounts. The point is, again, this looks like this could be, when you go through, like, look at all these word problems we have. These are not difficult word problems because students know what the procedure or the operation is going to be, and that's the hardest part, is trying to figure out the operation of it. And if we were to go through and say I was to change number 28 and just put there are 8 fish in the lake and 23 hot dogs on the table, that's just 2 phrases. It's not asking them to do anything. Half your students would just go through and they'd multiply it out and get 184 because we're not teaching them how to read and critically think through these problems. We're just using the problems really as an extension of the practice of the concepts. And again, when you go to our assessment, when we did our pilots in our schools, there's a 3rd grade class that we went into, and what were they working on? Multiplication, right? And guess what? When we showed them a simple, this is 9 red mints and 7 green mints, how many mints are there all together? A lot of students just mindlessly did 9 times 7 is 63 because that's how they've been taught. The word problem is always associated with whatever concept we're working on. Because this is a really easy schema or really easy type problem. It's just adding 9 plus 7. But students don't even know how to navigate through those problems, and that's why they're having so much difficulty with it. So remember when we went back to the brain imaging and what happens during word problems, the brain works the hardest in the planning stages. The way a lot of word problems are being taught right now, we're not requiring kids to do any planning because they already know what the operation is going to be. So they just pull out the numbers and then they're going through and they're multiplying that process procedure. And then when you look at the end, you're like, look, we did 20 word problems. What more can we do? But are we requiring them to actually think and plan through these problems, or are they just pulling numbers out? So unintentionally, we have transformed the purpose of word problems into mere vehicles for practicing mathematical concepts, where the emphasis is primarily on rehearsing the prescribed concept or procedure rather than engaging in genuine problem solving and understanding the intricacies of the specific problem structure. So why is a supplemental word problem program needed? And no matter what Gen Ed Tier 1 curriculum you use, it's just going to not work for some students. There's just not going to be enough depth or time or concept. So the idea is the word problem intervention program will act as a supplement, right, for your students because one, Gen Ed programs don't really do a good job of teaching kids strategies. It gives them a lot of word problems to solve, but doesn't really teach them how to attack those problems or logically go through those problems. See, the idea is you supplement with this, and as students improve their problem solving or their word problems within our program, it will transfer over into the Gen Ed curriculum as well. And remember, word problems, they're really not just difficult for your struggling learners. It's really, even if you're looking your Gen Ed Tier 1 students too, a lot of students in just Gen Ed Tier 1 struggle with word problems as well. So what we're going to do now is we're going to go through what the instructional sequence looks like of using the word problem intervention program. And what makes this different is, yes, this is our workbook, but with a lot of other programs that are out there, and maybe, we're going to get the workbook, we're going to go to the first unit, and we're going to teach the first unit for 2 weeks, and we're going to teach the second unit for 2 weeks. We're going to go through this workbook. And there's so many layers of instruction and sort of catalysts that go along that it is not just getting this workbook, opening it up and working. So this is more towards the end of the process when you actually start working at it than the beginning of the process. So we're going to go through step by step of what it looks like with our program, what the program's all about, what's the very first step, how does everything scaffold, how does everything layer, and then what's your final outcome and what is it you want to get to. So the first step in the process is administering the diagnostic assessments, whether you're using it for addition, subtraction, or multiplication or division. This is really going to be the catalyst. And what these assessments are going to do is they're going to allow you to really zero in on certain schemas. And you're going to realize as you give this assessment, some schemas are really easy for students and 80% of your kids do really well. And then you're going to realize that other setups or schemas less than 50% of your students can solve. So what this will allow you to do is go through, and then after you're done, you're going to be able to really track and look at, okay, result unknown, whole unknown, my students are doing pretty well. But any kind of problem with start unknown or, difference unknown is where my students are struggling. So it's going to allow you to be really efficient because you're going to be able to zero in exactly on what type of schema your students struggle with and then go to and instruct immediately that schema. So once you give the assessment data, what you're going to want to do is move into our schema cards or our movie posters, okay? This is a really fun, interactive way to introduce schemas to students. They really do like these. It's a lot of fun. And what it does is allows students to visually understand schemas and really you don't have to be a great reader and they're not going to be bombarded with a lot of text right away because our goal right now is to teach them about these schemas of the structure, okay? So you would go ahead and you have your posters and you put, you project your poster up onto your board and this one says 6 yellow glow sticks, 7 blue. How many altogether? And so you may not know, but this is considered a total part whole structure or schema. And so you would go through and you would teach students about, well, what are the parts? What are the parts? So they're identifying it and learning, okay, there's some prompts up there. There's 2 separate amounts. Is there anything changing or is it just we have 2 amounts and we're putting them together and they're learning about what that part whole is. So it's visual. There's not a lot of reading. It's a lot of fun. And this is a great way to introduce the schema. So then when you get to the next parts, right, students have some experience with what schema is before we're even going to start reading through, lengthy word problems and asking them to identify the schema there. So it's a great way to introduce it. Visually, it's a lot of fun and students really do enjoy this. So after you use the schema cards or the movie posters or the schema cards or the posters to develop that schema, then you go into our developing schema book. And this is where there's a lot of the different examples for it. And if you take a look at this, like the very first lesson for this one, this has to do with a numberless word problem. It says, there is a group of books on the table. There are some fiction books and the rest are nonfiction. So you'd go through and like, well, what is the whole? Well, there's no numbers here, so the whole would be the books on the table, right? And then we'd say some are fiction right here, and then the rest are nonfiction. So again, you're going through and we're using these numberless problems to go ahead and build the schema. And again, there's the prompts right here, and it tells you when you're done with this, where would you go in the actual, to do the actual lesson for it. And then the lesson after this, so it's like there's 2 parts to the lesson. This is your very first one. The second one now is the same exact problem, except now that there are numbers that are in this, so it's teaching them. So there are 10 books on the table. Oh, so the books were on the table. We know that this would be our whole right here. Some of the books are fiction and 6 are nonfiction. So we know that 6 are nonfiction and then we don't know how many are fiction. So again, it sets that schema up, then they're able to go through and understand it, and then we'll say, oh, we could set this up as a missing add-in problem. We could set this up as a subtraction problem. So again, many layers of schema. They have their poster cards. Now they're going through the numberless problem, then they're going into the actual word problem where they apply it, and all these layers of instruction again to get them familiar with the schema. So if you think about it, and again, when we first started doing this, we went through and we said a lot of people or a lot of programs, you'd be tempted to just grab the workbooks and start working on the workbooks right away. But there's a lot of scaffolding and schema development along the way. Now think you had your assessment, right? And then you did the movie cards and developed the schema through the visuals. And then you went through the numberless word problems, then worked into the word problems. After you do that, then you're finally ready to go into the actual workbook, okay? And with every single workbook, there's a slide for the first one, and I'll show you guys how this works. But this is what the teacher would have, projected and what they'd be doing, and they'd be working with it here. And then this is what the student workbook is. So the teacher would have this one that has all these other things that are built into it, and this is the teacher-led part, right? Teacher-led, the first problem is always done together. So teachers will go through, they're going to draw up the schema, they're going to solve it, and do everything with the students, and the students will go through and they'll practice theirs there too. And then there's teacher guided. The next one is the teacher will read the problem and just assist the students just a little bit and see if they're able to go through And then finally, you have that independent practice right there where every single lesson that you do with your students, at the end, they're going to have an independent problem that you could use as formative assessment or just, data tracking just to see how they're doing with it. Were they able to solve it? And so it's explicit direct instruction where you have a teacher-led, teacher-guided, where you're really hands-off. You're just helping them, just if they have any questions or maybe giving them a couple prompts. And then finally, you have the very last part too. So that's really what the instructional sequence looks like. We started with assessment, we went into the schema posters, then we went into the wordless problems, and then we got all the way finally to where we're now applying this schema and these graphic organizers to actual problems. And students it's also teacher-led, but it's also, we'll go to teacher-guided and also go to the independent practice. So let's just summarize. Remember, we talked about the themes in the research, okay? And we've gone over 3 of these, right? And the first one is explicit instruction on schema. You've already seen how our program really zeroes in and focuses and gives kids not just here's a problem, here's a schema, really developing and almost immersing them in schema, okay? Real world connections, we know that that's important. It says practice with a variety of problems. There are so many different types of problems that your students will encounter in our program. It's not just one, it's balanced. And for every easier structure, they'll be exposed to different structures as well. What we're going to cover now, the next 2 things we're going to cover is scaffold and differentiation. You're going to see how really efficient this program is at scaffolding differentiation. That's such a buzzword sometimes, oh yes, our program has differentiation. You're going to actually see how easy it is to differentiate within literally 30 seconds of a child having a struggle, and it takes very minimal planning and practice on your own too. And then finally, focus on a structured and flexible problem solving strategies. And so we're also going to introduce to you what our flexible and structured problem solving strategy is. And I know right now this is not a reading training or anything, but when you go through the science of reading, which is all the craze right now, and it's everywhere, but these things still can apply to math. You take a look at the things that science of reading suggests. One is a targeted approach. We absolutely have a targeted approach towards exactly the different types of word problems in the different schemas. Clear expectations through direct instruction. Teachers clearly explain concepts and model how to use them. We have very clear expectation. There's tons of modeling and direct instruction, explicit direct instruction that comes from the teacher. And finally, structured practice. Direct instruction provides opportunities for guided practice where students apply the learned skills. And as they go through, you'll have your teacher-led lessons, your teacher-guided, and then your independent practice. So those are all a big part of this program as well. And obviously, this is not a reading program, but the research from science of reading can also apply to our program as well. So we're going to go through scaffolding and differentiation right now so you can really understand the power and the thinking of how this program was put together, okay? So let's say you're working with some 3rd or 4th graders and you're working on a more difficult concept. It's called larger, smaller, quantity, unknown, and this has to do with it's a form of comparison schema, okay? So say you have this problem, and if you go through and you read this problem, this is a very difficult problem. It says David has 215 fewer marbles than Emily. David has 131 marbles. How many marbles does Emily have? So it's tricky because it's saying David has 215 fewer than Emily. We don't know how many Emily is, but David has 131. So you actually have to add 215 to what David has to get it. But because it has the word fewer on there and it's very confusing, your students may really struggle with this. So say you're doing this lesson and you're frustrated, your kids are frustrated, and like, I need to approach this differently. I need to make this more basic. So what happens is the way that this is, these are units that are all cross-connected to each other, okay? So if you're working with these larger numbers and your kids are really struggling, what you can do in an instant scaffold and differentiation and drop it down, or this could be you have some students, some special education students who just what you're working on with them is too hard and you need to drop it down to. So what you can do is you can say, I'm going to take this lesson and I'm going to break it back down to this quantity unknown to 10. So what you would do, you would go ahead and you go in, and if you take a look when you have your teaching slide, because remember this first teacher-led is always available as a projectable teacher slide, it's the same problem, except the numbers are much smaller. So it's David has 5 fewer marbles than Emily, David has 3 marbles. how many marbles does Emily have? So what you could do, you could literally take the problem, break it down even further, give them more visual supports, and you could actually do the same concept, because this is a concept which students are going to be doing in second grade, third grade, fourth grade, fifth grade. The schema stays the same. Obviously, the difficulty of numbers is where it becomes more difficult, and you could actually teach this lesson, scaffold it down to just solving it within 10, then taking the knowledge that they had from setting up this problem and have them apply it to that larger up to 1000, and this can really help them and give them the supports that they need when you're teaching that schema. So that's how differentiation works, and you could drop it down to up to 10 or up to 20 or up to 100 or up to 1000. But that just shows you the power of differentiation within this program, where you can instantly drop something back, work at it at a lower level. It's the same exact problems, just the numbers have changed. And it's a really strong, powerful tool that people can use instantly when your students start to struggle. Okay, so now we're going to go ahead, and we're known to do our pivots to readings during a lot of these trainings. So we're going to take a quick pivot into reading, and you'll see why I know this doesn't have to do with, well, because they're solving story problems, we must be, having to do something with reading. No, this has to do with what implementation of a strategy looks like, and two different types of implementation of a strategy. And this is a real story too. Back years ago, when I was a reading interventionist, I used a program called Orton Gillingham, and big part of Orton Gillingham is something called the cup strategy. Okay, so we're in a RT, back then it's called RTI, MTSS mostly called now, but RTI meeting, and the teachers kept saying, your intervention kids, their writing has improved so much. What are you doing with them? I said, oh, I use this cup strategy. They're like, oh, tell us more about this cup strategy. So, these weren't the exact posters we used, but we went back, and the teachers had their cup strategy, and they implemented it. And when they implemented it during their writer's block, which makes sense, right? It looks like it's a writing strategy. So they would go ahead and they were using it during their writer's block. And then when we came back like weeks later, like, it hasn't really made that big a difference. Their capitalization has gotten better, but, just it seems like it's not really working for us. And so to think about it now, well, of course it didn't work for them, because they were implementing that strategy in a much different way than I was. And though it looks like, yeah, we're both using the same strategy, I want to show you the difference. They're applying this just to when they're doing their writing, and I'm using layers of instruction. So you're gonna learn get a quick 1-minute recap on what Orton Gillingham is. But at Orton Gillingham, something called the 3-part drill. So we're gonna say we're working on blends. So the first part of the 3-part drill is kids learn how to read that blend in complete isolation. Okay. The second part now is called is where students do the writing of the blend. So then I would say the blend and they would write it. So first they read it, and then I say it, then they write the blend. Okay, and then we go back and they do blending, where they're actually blending that isolated blend into words and learning how to do that. And then there's something called dictation. And this is a really, really important part of why the strategy works so well too, is so you have everything that we did previously was supporting this dictation right here, where all these words have to do with the blends, the S blends that they're learning about, and then they write them. And then there's this part where it's called the dictation sentence, where I say a sentence to them, they go through and they write it, and then when we're done, we go through the cup strategy: capitalization, understanding, punctuation, and spelling. And remember, with the cup strategy, there's two parts: the capitalization and the punctuation. Those are pretty concrete type things. While the understanding and the spelling, those are more subjective, more open-ended type parts of the strategy, where kids are going to need a lot of support. So during this time when we're doing this dictation, we're talking about what understanding is, and we're having conversation. Oh, if this word was changed, would this make sense? And then there's a second sentence of dictation. I read the sentence to them. They go ahead and they write it, and then we do the cup strategy again together, talking about all parts of it: capitalization, understanding, punctuation, and then spelling. And then they go ahead and they write the sentence on their own, and they implement the cup strategy as well. Also, there's a part, there's red words, right? And red words are essentially sight words that can't be sounded out. And so we would work on red words 2 days a week. And the last part of the red words is they have to write their own sentence using that sight word. So again, that's another opportunity where we were really talking about the cup strategy. Particularly, this is a great time to talk about the understanding, because
Does that make sense? Oh, you wrote this. When I read it, does that make sense to you? So we're constantly supporting the cup strategy, even when we're not directly using it. We were doing things that would support that. Also, the last part too is there's something called the codable books, right? So if you're learning about S-blends and you're practicing S-blends, you're right about S-blends. Now you're reading about S-blends, and all these books are loaded with the sight words that you're learning about, and also loaded with the S-blends as well. So when you take a look, the reason why we had two different results from the same strategy is they were essentially using a strategy without the supporting curriculum in the training, right? They were just kind of using it as is. We're going to go through this acronym, and the expectation is this acronym is going to fix everything. I used the same strategy, but I was using a strategy that deeply engages the learner and supported by a comprehensive curriculum. So when we think about a lot of the math strategies we use, are we just kind of using it as is, or are we using it as part of a larger, more structured, more intentional curriculum? So now we're going to talk about the plethora of strategies that are out there, okay? And chances are, if you're looking at this screen, if you've taught long enough, you've probably used one or two or maybe even three of these strategies. And what typically happens is we were introduced to a strategy. Sometimes it's from another teacher, sometimes it's at a staff meeting, and then a decision is made. Okay, we're going to use this strategy. Usually there's not really much training for it. It's just, here's the strategy, or there's a 1 hour training or something, and then we go and we apply it. And then what happens is we're really excited about the beginning, and then we start to use it, and then it slowly starts to fade away. And then before you know it, you're not really using that strategy, and then someone comes up with a new strategy. So I'm going to give you some words of wisdom right now. There is no such thing as a magical strategy, okay? Every strategy is going to have its strengths. Every strategy is going to have its weaknesses. That's just how it is. And the point of it is what really makes a strategy has to do more with one, the teacher who's implementing that strategy, and two, the supporting pieces you have for that strategy. If you just have a strategy that's an acronym and you're just trying to apply it kind of randomly to all these different story problems, you're going to have difficulty with that. So, and here's just some points. No matter how brilliant a strategy is, if it's not implemented with fidelity, its potential benefits may not be fully realized. It requires commitment, dedication, and proper training. And essentially, you could go watch somebody do the cube strategy. You could watch three fourth grade teachers do it, and you could see it being implemented in three very different ways. So it's very important that if you're going to use a strategy, that there's training and that there's a commitment to it, and everybody understands what they're supposed to be doing. When there's no supporting curriculum, the success of a strategy completely rests with the quality of the teacher, not the quality of the strategy. A strategy without supporting curriculum can be like a ship without a compass. So essentially, when you do have a strategy, if you have a really good, knowledgeable teacher, they're going to be fine. They're going to be able to do it. But if you have a teacher who struggles or doesn't have a strong background in math, that strategy may not be implemented in the same way. An experienced teacher with a strong math background can take a mediocre strategy and get great results, while a mediocre teacher with a weak math background can implement a strong strategy and get poor results. So again, teacher quality really does matter a lot when you're using these strategies, especially when there's no supporting curriculum. And remember the cup strategy that we talked about with Orton Gillingham? The cup strategy may seem basic as an acronym, but it's like a recipe waiting to be used. The real magic happens when you add the supporting curriculum. It's the key ingredient that makes everything work. Just as a chef turns simple ingredients into a tasty meal, the curriculum turns a strategy into a successful learning experience. So, man, cups alone is not a great strategy. It's cups alone with the layers that Orton Gillingham provides makes it a really good strategy, and that's the difference. It's just an acronym without the curriculum. When you have all the pieces, it becomes something much more. And without the ingredients, most strategies are just an acronym.
So right now we're going to talk about the cube strategy, and there's a lot of different strategies that are out there, but I feel like the cube strategy, if you've taught long enough, is something everybody's probably used. And we're going to talk about what's kind of wrong with the thinking of it's just an acronym or a strategy. And first of all, we'll look at like, well, what is it people like? Like first of all, it's easy to remember, right? CUBES. It's predictable. It can be universally used across grade levels. And the first two steps are very easy. When you go through it, like circle the numbers, underline the question, box the keywords. So it makes sense. It's very structured and it gives kids who have no idea how to solve a word problem, it gives them some structure with it. Here's the sort of the downside of the cube strategy is it never actually tells you to read the problem or reread the problem. Teachers tend to focus too much on steps like circling, underlining, keywords, and so on. Has some very subjective abstract steps that students need support with, and it lacks support in curriculum. Like the cube strategy is a standalone strategy. It's not like a program. It's not something that's supported. It's just a strategy that exists. So we're going to take just a closer look at this. And remember, this is for any strategy that, there's cubes and foil, and there's a whole bunch of different ones that you can go through. But anytime there's a letter with a description of what you're doing, we're going to take a look at kind of what the downfall is and really why strategies like this don't really work. So we're going to take a look at the cube strategy with 3 different problems, okay? And we're going to see why, there can be some success with this strategy and also the shortcomings or why this may not be the best strategy, especially as problems get a little bit more complex and difficult for students, okay? But let's go ahead and read it. It says, Sarah had 45 friendship bracelets. She gave 12 of them to her classmates. How many bracelets does she have in total now? So if we go through and we follow the strategy, circle the numbers, we're going to go through and we circle the numbers, right? And again, people like the strategy because it's step by step and we feel like it's helping students, okay? Next, underline the question. We go through, how many bracelets does she have in total now? So we went through and we underlined the question, okay? We go through and box keywords, and the word gave is there. And so if in the cube strategy, there's a lot of keywords, and the word gave tends to signal some type of subtraction. So if we go through and we take a look at the cube's logic, the student's boxes gave, often a keyword for subtraction, in total. Since she gave them away, they subtract. The math is 45 minus 45 minus 12 equals 33. And the result is success. The keyword gave correctly identifies the amount being removed from the whole. So again, this is a strategy where people will use the cube strategy. And also, if you take a look, this was a change problem, okay? She had a bracelet she gave, and we're not talking about schema right now, but it definitely works with these result unknown, sort of easier problems to do, or easier schemas, okay? Now we're going to take a look at what the cube strategy used with another type of problem. Okay, so let's go through now. We're going to read this one. Remember, this is the cube strategy. We're going to use it just as it's intended, all right? It says, Sarah gave 12 friendship bracelets to her classmates. Now she has 45 bracelets left. How many bracelets did she have in total at the start? So this is known as a start unknown. It's a change problem, but we don't know what the start is. But let's go through and use the cube strategy and see where it leads us, okay? So we have, if we go through and we circle the numbers and we have 12 and 45. How many bracelets do you have in total at the start? Okay, that's our question. And then if we go through and we find our keyword is gave, right? So from everything that we know about this strategy and the keywords, this should be a subtraction problem. But we know that this is not a subtraction problem. So let's take a look where the cube's logic failed. The student sees gave and left and automatically subtracts. 45 minus 12 equals 33. But the math actually is 45 plus 12 equals 57. So the word gave, though it signals subtraction, it's not the operation which you need to do in order to solve this problem. So the failure is because the student is looking for the starting amount, the whole, they must add the 2 parts together. The keyword gave description describes an action that already happened, not the operation needed. Remember we talked about in the first problem, it was a result unknown, and that made sense is that a lot of times the cube strategy will work with those lower level result unknown for parts, for part, whole, or change. But when you have a missing part or a missing change, that's when the strategy struggles. So this would lead a lot of students to subtract, and the strategy didn't work. So we have 2 problems, very similar, and also on standardized tests, a problem like this is much more likely to occur than the first problem too. So let's take a look at what the cubes looks like in one more strategy. And here's the last one now, okay? And it says, Sarah has 45 bracelets. This is 12 more than the total number of bracelets her friend Maya has. How many bracelets does Maya have? And so if we go through and we circle the numbers, right? And we go through and we underline the question. So we circled our numbers. How many bracelets does Maya have? And there's 12 more than the total number. We know that more tends to be a signaling word. So let's take a look if the cube's logic worked. The student boxes more in total. These are classic addition keywords, and they calculate 45 plus 12. The math is 45 minus 12. The word more is being used to compare two people. Again, this is a comparison problem. It's important that students understand the schema of each one, because if they understand the schema, they'll be able to figure out the math. If they don't understand a comparison, a change, or result unknown, this is why these strategies such as cubes or FOIL or any acronym is really going to fail if it's not really looking at the schema and teaching kids how to logically look at it. So think, we had the cube strategy, we looked at 3 problems, and we had about a 33% success rate with it. And that was when it was using just the most basic result unknown or change unknown type problem. Once you get to missing parts, or this an unknown start or unknown change or an unknown part, that's when the strategy really begins to struggle, because the language doesn't always match what's going on. And we're going to take a look at these 3 problems we just did now in a few minutes at our strategy that we use, and how it can be a much different experience for students when you're focusing more on schema than you are on keywords. So there's a strategy out there that sort of was developed as the anti-cube strategy, because the cube strategy has such a high rate of failure for so many students, especially when the problems get more difficult. In the 3 reads protocol, it's read for context. You read it 3 times. First, you read for context, no numbers, no question. Then you read it again for the quantities and their relationships, and still no numbers, still no question. And then you read to determine what mathematical questions we could answer. So this is basically a strategy that was developed to stop the harm that was being done by the cube strategy. And there's a really good part to it. Like, one, it's you read it each time for a different reason, right? So you're reading it for context, and you're reading it for the relationship to the quantities. And then you're reading it to determine what you're supposed to answer, right? It focuses on language first, not the numbers, and relationships between the language and the numbers. The downside of this strategy is, one, the entire strategy is very subjective. Self-monitoring is involved. If you tell students to read the problem 3 times, they may read it, but each time they have to self-monitor. Oh, I'm reading it for context. Now I'm reading it for understanding. Now I'm reading it to determine mathematical equations and mathematical questions we can answer. It skews towards older students and requires strong metacognition, which means students have to be pretty good readers too. And it's a difficult transition from whole group to independent practice. However, the thinking of this is correct in you're not focusing on keywords, you're not underlining things, you're not circling things. The focus is really comprehending and understanding. So what we knew we had to do is somehow create a strategy that had the predictability and the structure of the cube strategy, because that's why so many people use it, because it at least gives your students something to follow along the way, okay? But also with using the 3 reads protocol, which is the ability to read for context and understanding and look for the relationships between the numbers and determine the mathematical questions we can answer, where you have one that's a very concrete strategy, this one's a much more abstract one. And what we did is we really blended the two to take the best parts of both strategies. And so what we came up with was the cub strategy. And no, it's not just the cube strategy minus the E, because these letters mean something very, very different. So the first one is they're reading the problem multiple times. So the first one is you read it and it says comprehend. Say what's happening in your own words. So before students go through and they start plucking out numbers, they're going to read it and you're going to ask them, okay, read this and tell me what's happening in it, okay? Then the next one, the U, is understand the schema. Reread the problem. And the problem is dealing with total, parts, change, compare, equal parts. And remember, this U is very difficult. There's a ton of curriculum that supports this. This isn't just a poster. There's a lot of curriculum and instruction that comes before you do this. If you just pull this strategy out and don't have the activities and the posters and the numberless word problems and build yourself up to this strategy is not going to work, because there's a lot of curriculum to support this. Then the next one is reread and build the schema. This is when they go through and they'll figure out what schema it is. They're going to use their graphic organizers, and then they're going to build the problem using the graphic organizer. Then finally, for the last part, it's summarize and solve, where they'll be taking the information from their graphic organizer, because they've identified the schema. They're going to figure out, am I adding, subtracting, multiplying, dividing? How do I figure this out? And again, I can't emphasize this enough. If you just take this poster and do not do the activities of building up schema and the understanding of it, it is not going to work, because when you get to the you understand the schema and build the schema, they're going to have no idea how to do this. So they have to have all the prerequisite, all the layers. We've talked a lot about layers of instruction. They need to have the layers of instruction in place before they can do this. So what we're going to do now is we're going to go through and we are going to work and use this CUB strategy. So the first part of the CUB strategy is we're going to go ahead and you're going to have the student read the problem. So go ahead, ready? Sarah had 45 friendship bracelets. She gave 12 of them to her classmates. How many bracelets does she have in total? So you would just go ahead and have a student say, okay, what's happening in the story? Well, Sarah made some bracelets and she gave some away, and we want to figure out how many she has. Okay, so that's the first part. The second part now is we're going to go through and it says reread the problem, understand the schema. Now remember, there's a lot of, you're not going to just going straight into a problem. You have a lot of curriculum that supports this. But is the problem dealing with total, parts, change, compare, and equal groups? So remember the word gave. We talked about the word gave and how that was a key word that we were using. And we're like, well, that's a key word and it meant subtraction. We're looking at this problem now. Yes, the gave is an important word, but it's not telling us it's subtraction. What it's telling us is that there was a change. So because we know that she had some bracelets and then she gave some away, that we know that this is actually a schema of a change problem. And we already know what the change is, right? So now that we've discovered it, we can go ahead to the next one, which is reread and build the schema. So we know this. We know that the change was 12. Okay, it says she gave 12 away, and we know that giving 12 away right there was subtraction. Okay, and it says Sarah had 45 bracelets, so we started with 45 and she gave 12 of them away, so how many does she have in total? So the word gave didn't tell us it necessarily subtraction, it told us change. Then we looked at the context of it and it told us that 45 minus 12, and we know that 45 minus 12 is 33. And that's how we used schema for this first one. So, and again, remember, the actual cube strategy worked really well for this one, for this problem as well. So, and the last part, don't forget, for this, we've already kind of done it. We'll go ahead and summarize. Our summarizing is, well, Sarah started off with 45. She gave away 12. We ended up with 33, and we could go ahead and 45 minus the 12, and we know that equals 33. Now let's see if our strategy holds up, and let's see what the next problem looks like. So now we're going to go ahead and we're going to take a look at this next problem again, and we're going to go through. Now remember, this is where the cube strategy struggled quite a bit. Okay, so it says, let's go ahead and read it. Sarah gave 12 friendship bracelets to her classmates. She now has 45 bracelets left. How many bracelets does she have in total? So we'll go through. All right, Sarah gave some bracelets to her classmate. She now has 45 bracelets left. How many bracelets did she have in total? So we're going to go through again. And if we take a look at this, though, we know again, we see the word gave. Sarah gave 12 friendship bracelets to her classmates. She now has 45 bracelets left. So again, gave isn't necessarily telling us subtraction. What it's telling us is, oh, there was a change in this problem. And the change was Sarah was giving something away. So we would go through, we explained, comprehend what was happening. Now we're going to go through and we're going to reread and identify the schema. And again, is this dealing with parts or change or compare or equal groups? And we know that from our experiences that that there was change again. Okay, so we'll go through and we know that the change was Sarah gave 12, so we know it's 12. So let's read it again. Now we have to build the schema. It says Sarah gave 12 friendship bracelets to her classmates. She now has 45. So after the change, right? After the change, she has 45. So 45 is now our end right here. So what we have to figure out is, now she has 45. How many bracelets does she have at the start? So we're trying to figure out how many bracelets does she have at the start. So we know this. She had some, right? We don't know how many, but she had some to start with. She gave some away, and we ended up with 45. So we end up essentially with a number minus 12 equaled 45. Now think about this. And when we're explaining this to our students, or your students are like, well, we don't know what this number is, but we know that we subtracted and got 45. So what we need to figure out is how can we undo this subtraction, right? What do we have to do to get back? We want to go from this 45. We want to get back to this. So if this number right here, we subtracted 12, what do we have to do? Oh, we have to go ahead and we have to add 12. So we would go through and we add it. And if we take a look, 5 plus 2 is 7, and 4 plus 1 is 5, and we went through. So again, the schema, we just filled in the schema and then we figured out, okay, and again, this is a difficult problem. But remember, the cube strategy, they'd all be subtracting. And there was subtraction involved in this, but it's all about, well, we have to find the missing part or the start, so the whole schema is different. So we went through the problem, we filled it in, and then we realized what we have to do. And again, the big part was identifying the schema, building the schema, and then we went through and able to figure out what operation, how we're going to solve this problem. Okay, so remember now we're going to go ahead, we're going to do this last problem. We're going to go through and we're going to read the problem. It says Sarah has 45 bracelets. This is 12 more than the total number of bracelets her friend Maya has. How many bracelets does Maya have? So we're going to go, remember, this is a little bit different now. So Sarah has 45 bracelets. This is 12 more. Now remember, if we were following the cube strategy or keywords, we'd say 12 more than the total number of bracelets her friend Maya has. How many bracelets does Maya have? And the important thing for this is we have to go through, we have to understand the schema right here. And if we take a look, though it's going to be tempting kids to say, oh, this is an addition. What we are doing, we are actually comparing. This is a comparison problem where we're comparing how many Sarah has to how many Maya has. So when we have two things that you're comparing in it, and we want to know how many bracelets does Maya have, this is actually a comparison problem. So we would go ahead now and we're going to go, we've identified that this is a comparison problem. Now this is going to help us understand, because remember for this particular problem, it says 12 more and your kids may be thinking, well, am I supposed to add? How do I go ahead and do I solve this? Okay. So we know this now. When we go through, now we have to go through and we're going to build the schema. Okay. So compare the greater. Well, what is the greater number right here? And it says Sarah has 45 bracelets. This is 12 more than the total. So we know that the greatest number we're dealing with is Sarah. And what Sarah has is Sarah has, I'm going to write Sarah in here. And Sarah has 45 bracelets, right? This is 12 more than the total number of bracelets that her friend Maya has. So we don't know exactly how many Maya has at all, but we do know that the difference, so we're going to go ahead and put Maya right here, and we don't know how many she has. We just know that Sarah has 12 more. So if we look at the difference, we already know the difference is Sarah has 12 more. So again, if Sarah has 45, right, we're building the schema, and we don't know how many Maya has, and we know the difference is 12. So now we have to go through, and we're going to go through, and we're going to solve. And we have 45, and the difference was 12. So we have to say, okay, if Sarah has 12 more than Maya, Maya has 12 less than Sarah. So we go through, we built our schema. We have the 5 minus 2 equaled the 3, and then the 4 minus 1 is 3, and our answer would be 33. And again, this isn't something where your students are going to do it day one and say, oh, that's a comparison. This takes time. That's why there's an immense amount of resources to help your students understand how to do this and identify the schema. And once they can identify the schema and figure out the greater, the lesser, the difference, and fill in the parts, it gives them a chance at solving these really difficult, more complex problems where the cube strategy just will not work for these, because a lot of these, the keywords, you're actually doing the opposite, so you have to logically break it down. And this is why the Cubs strategy is a very efficient strategy. And if you take a look, it's all about trying to identify the schema, right? And remember, it's not the strategy that's going to be great for the kids. It's that there's all the curriculum that backs up this strategy that's going to support them along their way. Okay, so now we're going to go through the assessment, and just so you know, when you get the assessment, there's 4 assessments within the addition subtraction. There's up to 10, up to 20, up to 100, and up to 1,000. So you're going to have to choose which one you feel is appropriate for the kids that you're working with. Obviously, your 4th or 5th graders, or they'd be, 3rd, 4th, or 5th graders, probably 100 to 1,000. First and second graders probably up to 10 or up to 20, or even your third graders maybe up to 20 as well. Because remember, this is more about the problem structures and how the word problems and the schemas work necessarily than what, the actual size of the numbers that they're working with. So the assessment has 12 questions. No matter what level of the assessment you give, it'll have 12 questions, and they're going to all measure the same things. Just obviously, the older the student is, the larger the numbers are going to be. So the first two questions that are on the assessment are known as result unknown. Okay, result unknown questions. And there's two different structures that are within them. The first one is a total combine or part on whole. And what that means is there's no action. It just says a candy store has 9 red mints and 7 green mints. How many mints does the store have altogether? So it just means there's a part 9 mints, the other part is the 7 green mints, and then you put them together, you combine them, that's a part whole. The second one is called a change result unknown. It says a beach vendor has 15 seashells. They sold 7 of the shells to a customer. How many shells do they have left? Obviously the change was, there's a verb, they sold 7. So that is the change, and again, we're trying to figure out what the result is. Data is going to show that your students will do best on these first two questions. The results unknown are the easiest one for students to get. When we get into other schemas and other structures, you'll notice that it'll fall off quite a bit, but these will be the two easiest ones that your students will solve. All right, tips for instruction, result unknown. One thing after you give your assessment, you're going to realize from your data that students will score the best on result unknown. They're the easiest problem structure, and we even looked when we were looking at using the cube strategy, how for result unknown, the cube strategy will work for that type of problem or those types of schema. Okay, let's go through total part whole. It says Jason has 25 pieces of candy, Sam has 43 pieces of candy. How many pieces of candy do they have altogether? So if you take a look, it's just two quantities existing at the same time together. There's no action happening. We're just saying, what do we want to do? We want to go through and we want to combine them. So you would just fill in the parts, and then talk about, well, we want to find them all together. What do we need to do? And you can work your way that way. Okay. So for change is different, though it's an easier problem as well. It says in a box there were 12 toy cars. 7 of them were taken out to play. How many toy cars are there in the box? So as we know, change means there's some type of action happening, an increasing action or a decreasing action. In this particular problem, 7 of them were taken out, so it's a decreasing action. So when we're setting it up, we're starting with 12. We know that we took 7 out, and what's our end result going to be? So here's some tips, and this will help you understand the difference between part whole and change when you're teaching that result unknown. The key question is, what is the total when we put these groups together? What is the final amount after the action? Okay, so again, even though they're both it could be both addition problems, it's different what's actually happening. The action are just sitting there. We are simply categorizing them. There is no action in part whole. The dynamic is something happens to increase or decrease the set. Relationship, both parts exist at the same time to make the whole. The relationship in a change problem is sequential. There is a beginning, a middle, and an end. There's the beginning amount, the change, and then the end amount. Typical problems combining sets, boys and girls, apples and oranges, indoors and outdoor plants. And for change, it's joining and separating, adding to a pile, eating snacks, spending money, birds flying away. And the standard equation is P1 plus P2, part 1 plus part 2 is going to equal your whole. And then for the standard equation for a change problem, you'll have the start plus the change, and that's going to equal your end result. So what did we observe from question 1, which was a part whole question from the assessment? I don't want to go through each question one by one, but obviously if it is outlined in green, it means the students got the correct answer. If it's yellow, it means they had the proper operation. They just didn't execute the calculation. And then if it's red, it shows that they just got it incorrect with the wrong operation or so on. So if you want to just pause this right now and take a look, because as you give this assessment, you're going to see all these different things as well. So if you want to pause it, take a look, and then we'll go on to our observations from number 2. And here are observations from question number 2, which was a change problem. And again, if it's in the green, it means that student performed it correctly. Yellow means they had the proper operation, but they just didn't get the correct answer. And then red would be there's some type of misconception or they didn't do the proper one. But if you want to go ahead and pause it, and these will be all things that you will see as you give these to your students as well. So now we're going to go through the second part of the assessment, the next set of questions that's on it, and it's change part unknown. Now this is going to be more difficult because these aren't straightforward as for the first two questions, which had to do with two parts being put together and adding them, or there being a starting point and then there's an action. This is a little bit different because what you have a piece of information, you have a missing piece, and then you also have the end result or you have the total. So this is more difficult for students to do. Just to understand this type of thinking, you have to develop it, and kids need experiences before you ever even get to these word problems. So this is from our primary numeracy intervention program, and this is that type of algebraic thinking or missing part or part whole thinking that students have to develop. And if you take a look, a lot of it has to do with scaffolding, where there's images and pictures and students are having multiple experiences with that. And then finally, again, they're working with the digits. So they need to have this in place before you can ever even get into these two problems. And let's take a look at this problem too. It says a school has 16 folders, 7 of the folders are red, the rest are blue. How many blue folders does the school have? And we know that that is a part whole missing part one. And it says Lily had 13 candies. Tim ate some of the candies. Lily now has 8 candies. How many candies did Timmy eat? What we're solving for is the change. The change is unknown. So there's a part unknown here and a change unknown here. So we're going to go through two different types of change problems right now. And one is change unknown increasing and one is change unknown decreasing. Okay. So obviously when you're going through, you know that you'll be doing the Cub strategy with your students. So I don't want to focus too much on that. We spent time on that. This is just more the teaching points too. So Lisa had 8 stickers. She bought some more stickers at the store and she now has 12 stickers. So we know that she bought some more. And so that's going to let us know this is definitely going to be a change problem. So let's go through again. Lisa had 8 stickers. She bought some more stickers and now has 12 stickers. So when we go through, we have our starting point of 8. She bought some more stickers and now has 12. We don't know what the change is. And we know that the end result was 12. So when going through, and once you set this up now, you're going to have some options for your students, right? The first is you could go ahead and say, well, we have 8 plus something equals 12. And you could set the equation up as a missing factor. And remember, this is this is only going from 8 to 12. So this is something that could easily be set up as a missing factor, and they just go 8, 9, 10, 11, 12. Also, you want to show them too when you're doing this, you could solve it this way, but you also can set it up as a subtraction problem because if we're starting at 8 and we added to get to 12, we can go ahead and we subtract 12 minus 8, we can figure out what that change was. Also, it's important to realize when you're teaching kids strategies, where are you going to add through missing add-in or subtraction? Just remember this. And not too far in the distant future, they're going to be dealing with 3-digit numbers. To set up 148 plus something equals 452, that's really hard to solve kind of on the fly as a missing add-in part, because it's just, from here you're going 8 to 12, you can count up. From here it's much, much different. So you do want to make sure that if you're going to show them that missing add-in way to solve, you also show them the subtraction, because when they get to the larger numbers, they're going to have to subtract. Okay? Let's take a look at the next one now. Change unknown decreasing, okay? So if we take a look here, Tom had 13 cookies. He ate some cookies and now has 8 left. How many cookies did Tom eat? So again, we know that he ate some cookies and has 8 cookies left. So we know again that there was a change in this problem. If we go through, we started with 13. He ate some. We have no idea how many he ate, but we ended up with 8. And again, when going through this, you could set this up for, with your start, something, we have 13, something happened, and it equaled 8, so it could be 13 minus something equals 8 is the equation. Then have your kids understand, if we need to find out what that number is, if we're going from 8 to 13, how would we figure this out, or how would we figure out that difference between the two? And we would just do 13 again minus the 8. So once you have your schema graphic organizers filled in, you'll have some options for how you want your students to actually solve it. So you want to show them different strategies, different ways that they can do it. And now we'll go through part unknown, the first part, and part unknown whole first, okay? So if we read through the problem, there were 7 apples in a basket. There are some more apples in a bucket. There are 12 apples in total. How many apples are in the bucket? Okay? So we know that again, there's two things that exist at the same time. There's a basket of apples, or there are apples, and there are some more apples in a bucket. So there's apples in a basket, apples in a bucket. We know that this is part whole. Okay? Now, up to this point, most of your students are used to filling in when you fill out this graphic organizer. It's going to be part and part. But for this one, we know that there are 7 in one part, and then they're telling us there are 12 apples total. So when we fill out the graphic organizer with our students, it's like we have 7. We know the total is 12. Now we have to figure out what's that missing part. You have a couple of different options. One you could set up as a missing add-in. We talked about it's okay when the numbers are small to set it up as a missing add-in. But as the numbers get larger, it's going to be more difficult for them to figure that out. Also, if you do set it up as a missing add-in, also show them you also can subtract, okay? And now for this next one, part whole, first part unknown, okay? So it says, a card show has 18 trading cards. So this one starts giving the total first. 7 of the cards are baseball cards. The rest are football cards. How many football cards does the card show have? So again, if we set it up and we go through, we know that we have 18 trading cards. Our whole is 18 cards. 7 of the cards are baseball cards, and the rest are football cards. So again, once you have the schema identified and the graphic organizer filled in, we have to figure out, all right, we have 7. We got to figure out from 7, how are we going to get to 18? You could set it up through a missing factor. 7 plus something's 18. Or you could just subtract. And these will be the first problems that are more difficult for your students. So, and a lot of times when you transition to the instruction part, because you're going to teach part missing, result unknown first, and so they're going to want to go ahead and plug everything in where part where you're explaining, no, we're actually putting in a total, and this is a scaffold, but this is very useful to help students when they're solving these types of problems. And what did we observe from question 3, which was a part whole, missing part? Again, if you want to go ahead and pause it and just take a look, all these things that you're seeing from our pilot school, you'll also see in your own school as well, but you just want to take a look at what to expect. Go ahead and pause it and you can take a look at those. And what did we observe for question 4, which again is a change unknown problem. So again, if you want to go ahead and pause it, you'll see a lot of different strategies, particularly when the problem structures or schemas become more difficult. You'll start to see students getting the answers incorrect more, and also using inappropriate strategies or operations as well. So the next problem structure in which we're going to talk about is start unknown. And start unknown is like, it's part of the family of, part whole with a missing part, or a change problem with a missing change. It's just the first part's going to be missing the start, and so it's like a micro step. So it's still very similar thinking to what they did for 3 and 4. For this one, these both actually are change problems. If you take a look, it says Ruby had some balloons. Trey gave her 5 more. She now has 14. How many balloons did she start with? This is a change, and it's an increasing change because she was given some more, and so we're trying to figure out the start. Liddy had some rocks. She gave 6 to Tommy, so this is a decreasing change. So we'll go through and take a look at what this looks like. But again, when you're solving start unknown, very similar to how you would do sort of part whole missing part, or change missing change, or unknown change. Very similar to that type of thinking, just like a micro step really of just doing a slight change or a little bit different beginning point for the equations. Okay, and these problems are very similar to the ones that we just did from the assessment, except instead the missing part's going to be the start, okay? So let's go through and read this. It says, Alex had some marbles. Mia gave him 5 more. Alex now has 15 marbles. How many marbles did Alex have initially? And again, that means initially, or how many did he have to start? So when we go through, the big thing is he gave, we can identify that as a change. And then it says Alex has some marbles. By this point, when you hear some or a few, kids should know that those are words that really mean like it's missing, it's unknown. We don't know what it is. So if we go through and we fill this in, Alex had some marbles. We don't know exactly how many are at the start, but we know that there were some. Mia gave him 5 more, and Alex now has 15 marbles. So we've discovered, yes, this is a change with the start unknown, and now we have to say, okay, we have a number. We added 5 and we got 15. So again, what are our ways, what are our methods to go through? One, you could set this up as a missing add-in problem. We've talked about when the numbers are smaller, a missing add-in makes sense because you can still figure it out without it being very lengthy, but you also want to show them that you also can go ahead and you can subtract to find these. Showing them both methods is absolutely fine. All right, let's take a look at the next one now. It says Benjamin has a few black magnets. He also has 8 green magnets. He has 14 magnets in total. How many black magnets are there? And remember now, so we have some a few black magnets, and we have some green magnets. There's no comparison going on. There's no one else in the problem, right? It can't be comparison. It's not a change. There's no action or verb or anything that's increasing or decreasing. So we know this is part whole. And again, Benjamin had a few black magnets. We don't know how many were in that first part, right? But he also has some green magnets, and he has 14 magnets in total. So again, we have it set up. We have our total. We have 8. We have to figure out what goes with 8 to make that 14, and how can we make this work? And again, you could set it up as something plus 8 equals 14, or you also always want to make that subtraction connection of 14 minus 8 to do that. Okay, and again, this is not going to be much different from the change unknown or a part unknown from earlier. It's always going to be at the beginning, so it's like just a smaller step in which you're going to be used to set up the problems. And what did we observe from 5 and 6 from our pilot? And if you go through, as you get to these more difficult problem structures or harder schemas from within the structures, you're going to notice students start getting the answers wrong more. You're going to see more different types of strategies that are used, some correctly, some incorrectly. So go ahead and pause it and just take a look, and you'll see a lot of these same things will be done with your students as well. Okay, in the entire second page of the assessment, they are all comparison problems. The first 2 have to do with the comparison where the difference is unknown, okay? And so we'll just take a look. It says the Pirates scored 17 points in a season. The Rams scored 9 points in the season. How many more points did the Pirates score than the Rams? So again, this is a comparison where we're trying to figure out what the difference is. We know how many other Pirates have. We know how many the Rams have. Just what's careful is how many more. Again, a lot of students will see the word more and they're going to think you're going to have to add, but you're really trying to go through and find the difference between those two. All right, and for this one, it says Lucia has 13 pencils, Jada has 5 pencils. How many fewer pencils does Jada have than Lucia? So sometimes, like the word how many more, how many fewer, kids may not understand it. But because it says fewer, kids may say, like, oh, fewer means subtraction. So kids may be more likely to get this one right without understanding it necessarily, just because the word fewer kind of tipped them off to like, oh, fewer must mean subtraction, even though you're going to be subtracting for both of these. If the word many more may have kids thinking, oh, I need to add to figure this one out too. So, all right, and we'll go ahead and we'll take a look at what it looks like when you're instructing these ones. So all of these problems here have to do with comparison and the difference unknown. We'll take a look at the structure, what it looks like. But it says Chloe has 10 balloons, Liam has 17 balloons. How many more balloons does Liam have than Chloe? This is your standard comparison, right? For comparison, you have to have two people or places or something that you're comparing. So right away, it's like, oh, and also the tip, how many more balloons, how many more is often lets you know, yes, there's definitely going to be a comparison going on. So all you have to do is go through here, and this is once you identify the schema, it's pretty easy because, okay, who has the greater amount? Liam has 17 balloons. Chloe is the lesser amount. And what we're trying to do is trying to find out the difference. We know that Liam has more than Chloe, so we just need to know what that number is, and again, how we go through and do it. Again, one way you could set up as a missing add-in 10 plus something 17, but you really want to get to that subtraction, understanding that 17 minus the 10, and what's the answer going to be? The answer is going to be 7. So again, comparison, really easy to fill it in once you understand the schema because you just find the greater and the lesser. Okay, let's take a look at the next one. Isabella has 18 apples, Mia has 10 apples. How many fewer apples does Mia have than Isabella? Again, it's a comparison, how many more, how many fewer, and there's two people, me and Isabella, so again, we know it's comparison. And again, we know Isabella is our greater, has 18. Mia has our lesser, 10, and our goal, or what do we want to do, is we want to find out how many fewer apples, and we have to figure out the difference. Again, a couple ways you can do it. You could always set it up. 10 plus something equals 18. Also get to that subtraction of 18 minus 10 equals. So for comparison, difference unknown, pretty easy to set up. Once you have the greater and the lesser, then you're just teaching them to find the difference in between. And here's just some things we observed from our assessment pilot that we did in one of the schools. And you can go ahead and pause it and take a look. Obviously, if it's a green, it is correct. And if it's in red, you'll see that there's some misconceptions, or sometimes they just did the math incorrectly. But go ahead and pause it and take a look. Okay, so the remaining 4 problems, these problems are similar but also different to each other, so we'll go through and you'll see why students tend to do well with some of these and struggle with the other. So for this one, these are all still comparison problems, where for 7 and 8 you're solving for the difference. This time you're solving for the larger quantity or the smaller quantity. So it says Jackson has 14 pretzels. Gio has 4 more pretzels than Jackson. How many pretzels does Gio have? So you're solving for the greater quantity, because we don't know that Gio has a greater quantity, and 14 plus 4 is going to equal 18, so you would go ahead and solve it. And again, Gio has 4 more, and that 4 more matches, like, oh, we're going to go ahead and we're going to add here. Now this one's a lot different. Number 10's a lot harder. It says Will has 5 fewer acorns than Jay. Okay, so Will has 5 fewer than Jay. Will has 15 acorns. How many acorns does Jay have? So we're off the bat, we know that Will has less than Jay, and they're telling us how many Will has. So if Will has 5 fewer than Jay, it means Jay has 5 more. So this is confusing to kids because the word fewer makes them think subtraction, but you actually have to break the schema down and understand what you're doing. You actually have to add. This one's similar. Emily has 16 bracelets. She has 4 more bracelets than Violet. How many bracelets does Violet have? So we're this one, we were solving for this one right here. We're solving to find out who has the lesser amount. We already know Emily has 16 bracelets, and we know that she has more than Violet. But that more makes kids think that you have to add, but actually when you break it down, you have to subtract. So these two are very, very confusing, because they see fewer and they think that you are going to have to add, and then they see more and they think you have to subtract. So it's really a language thing. And then this last one, it says Rio has 4 fewer books than Kurt. Kurt has 13 books. How many books does Rio have? So this one, again, it matches, where you're like, oh, 4 fewer. If you just go with subtraction, you'll get this one right. So kids tend to do better on number 8 and number 12. Number 10 and number 11 are more difficult for them. Okay, so now we're going to do comparison and solving for the larger or greater quantity or smaller quantity. The last comparison we did is we were focused on the difference. These types of problems, you're given one of the quantities and the difference, then you have to figure out the other one. And these are really tricky, so you have to read them a couple times and really think. There's a lot of logic and thinking involved to these. This is Lucas has 7 cookies. Lily has 7 more cookies than Lucas. How many cookies does Lily have? Well, we know that we're comparing how many they have, right? And we're comparing what Lucas has with what Lily has. We're trying to figure out how many Lily has, okay? So again, Lucas has 7 cookies, and Lily has 7 more cookies than Lucas. So Lily doesn't have 7 cookies, she has 7 more. So we know that Lucas's cookies are the lesser amount for this one, okay? And now we have to say, okay, Lily has 7 more cookies than Lucas. So we know the difference also is 7. And we also know that we don't know exactly how many cookies does Lily have. That's what we're solving for. So when we set this up, we would go ahead. We know that it'd be 7 plus 7. What makes this problem, I don't want to say easier, is that it's telling us Lily has 7 more cookies than Lucas. So it tells us right there, if she has 7 more, we know we're going to be adding to what Lucas has. Okay, let's take a look at this one now. Ava has 8 fewer balloons than James. And it's important. She doesn't have 8 balloons. She has 8 fewer than James. And James has 15 balloons. How many balloons does Ava have? So we have to go through and figure out, all right, do we know the greater or the lesser? Well, we know. It tells us right here, Ava doesn't have as many as James. We know James has 15, okay? It also says Ava has 8 fewer balloons than James. So she has 8 fewer, 8 fewer, then we already know the difference between those two is. And so then how will we go about in solving it? And we go ahead and go 15 minus 8, so we're solving for the lesser. Again, both of these are easier. I don't want to say easy, easier to solve because that language of more and less leads you, more leads you to addition and less leads you to subtraction. Now, the next page will be a little different. So these last two problems also have to do with solving for the larger or greater quantity or the smaller or lesser quantity, but these are very confusing for kids. So let's take a look at the first one. And it says, Ella has 17 pencils. Ella has 5 more pencils than Liam. How many pencils does Liam have? And as you can tell already, you can see what's tricky for kids is we already know what the greater is. Ella has 17 pencils, and they're telling us Ella has 5 more pencils than Liam. So if she has 5 more pencils than Liam, right? So we know the greater is 17. Now we don't know how many Liam has, right? But we do know the difference is 5. So the difference between what Ella has and what Liam has is 5. So what we're doing, we have to solve for the lesser, and we don't know what the lesser is. And why is this so difficult? Because it says Ella has 5 more pencils than Liam, but we have to subtract. So that more throws kids off where they think, oh, we're just going to be adding because it's more, but you're actually subtracting. And this problem is the opposite. Let's take a look. Ava has 8 fewer chocolate bars than Mia. Ava has 12 chocolate bars. How many bars does Mia have? And this isn't supposed to be there, but it's already there, so that's the reveal. But if we take a look, okay, we know we have to figure out, okay, Ava has 8 fewer chocolate bars than Mia, and Ava has 12. So we know that Ava has 12, and we know if she has 8 fewer than Mia has more than she does. So we know what the lesser is, 12. We also know the difference is 8. It's just getting to the point where students understand, okay, if Ava has 8 fewer chocolate bars than Mia, it means Mia has 8 more than Ava. It has 8 more than Ava. So that's the difficulty part with this. And this is why students struggle, because the language, they're doing the opposite of what they think they're supposed to do, because it has more. When you have a problem that has more and you actually have to subtract. And then you have a problem that says less and you actually have to add. So very difficult for students. And also these are the types of questions they love to put on standardized tests. So making sure your kids understand the schema, right? Making sure they know how to fill in the graphic organizers and help organize their thinking. And again, from the pilot, these are just some of the answers that you'll see. And as you give these, you're going to see your students adding, subtracting, some may multiply, and so on. And this is for 9, 10, 11, and 12. And next page, there's a couple more. And here's a few more on this page as well that you can go through and just take a look at the types of errors kids are making. And you'll see a lot of your students doing these same things. Okay, so the assessment is well designed, and it does a very good job of measuring what you want to do, and making sure your kids understand different structures or different schemas within word problems. Something you need to keep in mind is this assessment also is just going to be a snapshot in time, okay? Especially when you're giving the addition subtraction assessment, because kids can still get these right and not understand why they got them right too. Because if you're giving addition subtraction one, a lot of students are already going to know I'm adding or subtracting, so they have a 50% rate of just kind of guessing if they're adding or subtracting and getting it right too. So just keep that in mind. You want to have this be some data pieces, but you also want to observe your kids and give them exposure to problems too. So even if when you give your assessment and you have students who maybe tested well on an area, I still would spend a little bit of time instructing it, because you just want to make sure they have that depth there too. Because remember, the assessment's a snapshot in time, and the results need to be interpreted as a snapshot. If a student adds every time, they'll get 4 out of 12 correct, right? If a student subtracts every time, they'll get 8 out of 12 correct. So many students will know addition and subtraction, so if they guess or confuse, they have a 50% chance of getting the correct answer. So just because they got a correct on the assessment doesn't mean that they necessarily understand that schema. So you want to really be balanced with your instruction. And when you're going through your instruction, you're like, well, the kids, they did really, or this particular group of kids, they did well with change unknown. I still would spend a little bit of time of instruction doing that to make sure they have that depth. It says students can misinterpret language and fall into the correct answer by chance. And we spend a lot of time how more can still mean add and also can mean subtracting too. But if kids are using low-level strategies or just latching on to these keywords, they'll get it right by chance sometimes, but they're also going to get a lot wrong too. And the assessment should be a factor in planning, but not the only factor too. So this is going to give you some data to start with, but I still really would unit by unit go through and instruct. And obviously for result unknown, you may be doing it for 1 or 2 days and say, okay, my kids really have this one. We need to move on. But just make sure that you stay really balanced, and the assessment can be misleading sometimes if kids can get ones right that they really had no business getting right too. So just keep that in mind too.
So what will this look like in the classroom? So there's a lot of ways that this can be used. And the first one is whole group supplement for general ed, 10 to 12 minutes a day. If you are a third grade teacher, this could be how you start your day, first thing in the morning, the 10 minutes before lunch, the 10 minutes after lunch, the 15 minutes you have in between art and music class. So there's times where you can go ahead, and this could just be a supplement for an entire group, and it's just what you do to supplement your gen ed curriculum. Whole group intervention block, that win time. There's win means what I need. And so this word problem program truly could be an entire curriculum for one of your win groups or all of your win groups going through and working on that time, because problem solving is something that all kids need too. So this is something you could do in a whole group. Small group pullout, individual student pullout too. So if you have small groups kids are pulled out for intervention, this works great for them as well. And obviously, and this is great for special education goals too. So for special education kids, problem solving is very, very difficult. And this is just a sample of a goal that you could write if you're a special education teacher that really uses the problem. It'll give you your measurement. You have all your measurement pieces in there. You have that pre-test that you can give to. And so it's really a good thing to use for special education goals too. Can the word problem program replace the other programs? And the answer is no. And here's why. However, right? The primary program works on developing basic numeracy and number sense, okay? However, it does scaffold its way through, so eventually your students will be working with more abstract numbers, right? And when you're doing something like this, what you're able to do is when your students are done and you're confident with them, you can say, okay, now I want them to apply it. So you go in, addition, subtraction, change unknown, and you can go ahead and start working with them on this. So the word problem program definitely can be used alongside with the primary program. It's just not designed to ever be a replacement for the program, okay? And then so you could say, Monday, Tuesday, Wednesday, or how many days a week. So say Monday through Thursday, we'll work on the primary program, and then we'll do problem solving on Friday.
So this is just a suggestion. This is just showing you how the program is really meant to be a K through 5 program, how you can keep adding to it too, and how each part builds upon each other as well. And understanding that your students are going to be exposed to these types of word problems and schemas all the way through. What's going to change though is obviously a kindergartner result unknown is going to look different than a fifth grader result unknown because of the size of the numbers. But those schemas, those concepts stay in place too. So don't think like, oh, we're going to do a 12-week intervention for word problems and everything's going to be fixed, because this is meant to be really both a vertical and horizontal type program that exposes your kids to different problems. So if you're looking at it too for how you want to do it, again, this is just a suggestion. You could have your kindergartners really zeroing in on result unknown and teaching them about the result unknown, the schemas that go with the result unknown. Then in first grade, you could add another layer of it. Of course, it's going to be a little bit harder problems, and then you could add some more schemas. Then by the time they're in second grade, they'll be learning about all the different schemas in third grade and fourth grade. So the idea of this is your students are getting all these different this instruction, the exposures, and then each year you're building and adding to it. So then by the time I had students in third grade, they've had years of instruction and schema. And so don't think of it like, oh, my kids are learning these schemas in 12 weeks. It's going to take them a while to learn and understand. Then by the time they get to those third, fourth, and fifth grade, and what happens in third, fourth, and fifth grade, that's where a lot of students start taking those standardized tests. That will be there as well. So one thing of advice is remember this. It's a marathon, not a sprint. This program has the end in mind, you could say, or it really is the long game for this, where it's going to give kids lots of exposures year after year after year to different types of problems, where they will then become really efficient problem solvers. And if you're wondering how to get your free materials, all you have to do is go to numeracyconsultants.com. And if you scroll to the bottom of any page, you'll see this blue copyright where it says, copyright 2026 Numeracy Consultants LLC. If you go ahead and click on that, it will take you to all of our free materials. And then you just go through, you find the problem you want, you would go ahead and click on the that button right there, and that will take you to all the free materials where you'll have the read alouds and assessments, and the units from the books and everything else will be there. Okay, and this is the end of part one of this. Part two will be very, very short. It's probably about 30 to 45 minutes, and it's just going to go through it's not going to be as in-depth as this one. It's going to just go through the multiplication, division structures book and through the multi-step problems as well. And this will be available when you go to the materials page. It'll have both part one and part two. The trainings will be at the very top of the page. When it's ready and posted, it'll just be up there. It'll be the one on the right. You can go ahead and click on that. It'll be about 30-35 minutes for just to go through the materials for that.